Okay, so hi everybody, welcome back. Today we're going to finish up our chapter 36 lecture on the theory of relativity, and where we left off last time was a discussion of relativistic dynamics, which includes the famous equation E equals mc squared. So let's continue on with that and do an example problem. So when you heat up a pot of water, you increase the internal energy of that water. According to the theory of relativity, this will cause the water's mass to increase as well. So let's suppose that you have 2.50 kilograms of water initially at 20 degrees Celsius, which you heat up to 90 degrees Celsius. By what amount does the mass of the water increase in units of kilograms? So one thing you're going to need to know to do this calculation is the specific heat of liquid water. That's 4,186 joules per kilogram per degree Celsius. So try to work this out, pause the video, see if you can get it, and then we'll go through it together. Okay, so we'll start with the idea of rest energy, which is given by E naught equals mc squared. Now remember, the idea here is that rest energy is the energy an object has just by existing in its current state. It doesn't depend on how fast the object is moving or how high off the ground the object is or anything like that. The rest energy just is what it is. So if there's going to be a change in rest energy, if there's a delta E naught, that's going to have to correspond to a change in mass, because on this side of the equation, on the right side, we have m times c squared. C is a constant. The only thing that can change is m. So delta E naught is equal to delta m times c squared. So again, any change in rest energy is accompanied by a change in mass. These things are equivalent in some sense. Okay, now let's think about the pot of water and how that kind of fits into this picture. So here's the pot with some water in it. We're just going to look at the water itself. That will be the system under consideration. And that system has some sort of rest energy, E naught. But the idea is we're heating the water up, so we're letting some energy flow into the water from the outside. So if that heat is absorbed by the water, it's going to increase the rest energy. Okay, the heat that flows into the water increases the rest energy. Of the water. Okay, and therefore increases the mass. That's really the whole idea behind this problem. So if we take that statement that the heat that flows into the water increases the rest energy of the water, we can turn that into an equation. Q, the heat that flows into the water, is equal to delta E naught, the change in the rest energy. Now let's remember Q is equal to the mass of the water times the specific heat, which I'll write as CH2O. So CH2O is 4,186 joules per kilogram per degree Celsius. And then that gets multiplied by delta T. That's the heat. That's equal to delta M times C squared. So just so we don't get confused, C without the subscript is the speed of light, which is 3 times 10 to the 8 meters per second. Now what we want to do is find that change in mass. We want delta M. So that's going to be M times the specific heat of water times the temperature change over the speed of light squared. Okay, now before we even make the calculation, I just want to point out that delta M, the change in mass of the water, is going to be tiny. And the reason for that is the speed of light, c, is a huge number, and we're squaring it to make it an even bigger number, which is in the denominator. So we're dividing by a gigantic number, we're going to get a small change in mass. That's why changes in mass under normal circumstances are very hard to notice. They tend to be very small. So anyway, let's make the calculation. On top, we have M. The mass of the water is 250 2.50 kilograms. The specific heat of the water is 4,186 joules per kilogram per degree Celsius. And then the temperature change is, well, the final temperature is 90 degrees Celsius. The initial is 20. So 90 degrees Celsius minus 20 degrees Celsius over the speed of light, 3 times 10 to the 8 meters per second, all squared. So if you calculate that, you get 8.139 times 10 to the minus 12 kilograms. And we round that to 3 sig figs to get 8.14 times 10 to the minus 12 kilograms. So yeah, that is a very small amount of mass, about 1 trillionth of a kilogram, which is roughly the mass of one bacteria, just to give you a sense of scale. So again, it's a tiny little increase in mass. It would be very hard to even measure this, but it is there according to Einstein's theory of relativity. And as I showed you before, in other contexts, like in nuclear reactions, the change in mass can actually be pretty significant. So that's how this works. Okay, so next, we're going to derive a really important relationship between energy and momentum. And we're going to start with the expression for relativistic energy that we found in the last video. Now, this is the total energy E. It's the sum total of an object's kinetic energy and its rest energy. And this total energy E is given by gamma times mc squared. So we found that in the last video. So I'm going to do some manipulations to this equation. I'm going to start by squaring both sides. So we have E squared is equal to gamma squared times m squared times c to the 4th power now. And what I'm going to do with that c to the 4th power is split it into two different terms. So we have E squared equals gamma squared times m squared times c squared times another factor of c squared. Okay? What I'm going to do next may look a little bit strange, but trust me, this is going somewhere. So I'm going to leave the left-hand side the same, and then I'll leave the first 3 terms on the right side the same. We have gamma squared, m squared, c squared. But for that last factor of c squared, I'm going to write it this way. I'm going to write it as c squared plus v squared minus v squared in parentheses. So of course I can do that. V squared minus v squared is just 0, so these are equivalent expressions, just expanded out. Okay, so the next thing I'll do is I'll take what's in the parentheses here and focus on the second term. So if I distribute this term out front into the parentheses, I'm going to have gamma squared, m squared, c squared times v squared, just to pick this term out. So I'm going to put this out front. We have gamma squared, m squared times c squared times v squared. And then I'll leave the rest of it alone. Gamma squared, m squared, c squared out front in front of the parentheses, and then we'll just have c squared minus v squared because we've already gotten rid of that middle term. Now, the next thing I'll do is I'll take the first term on the right side of the equation, and notice I have gamma, m, and v all squared. So what I'll do with that is just write gamma mv in parentheses and then square that whole expression times c squared. And then for the second term over here, what I'm going to do is pull out a factor of c squared from the parentheses. So we'll have gamma squared, m squared, now c to the 4th because I've pulled out a second factor of c squared, which means now in the parentheses, I just have 1 right here, and then minus v squared over c squared, okay? So here's where this pays off. We're going to sub in some expressions that we've developed earlier in this lecture, specifically for momentum and the gamma factor. So we recall that the momentum in relativistic terms is given by P equals gamma mv. Well, I have gamma mv right here in the parentheses, so I'm going to sub in P for that. And then we remember that gamma is equal to 1 over the square root of 1 minus v squared over c squared. So I'm going to plug that in for gamma right here. And here's what we get. E squared is equal to P squared C squared plus, so we have the gamma squared here, which means I undo the square root, 1 over 1 minus V squared over C squared. And then I have M squared C to the 4th here. And then 1 minus V squared over C squared. But here's the thing. This term in parentheses cancels with this term in parentheses. So now we have something really simple. We have E squared is equal to P times C, quantity squared, plus MC squared to the second power. Okay, that's how we can write our final result right here. So if we take a look at that final result and we plug in 0 for the momentum, so P is equal to 0, well, the entire first term on the right side of the equation goes away. And then we just have E squared equals MC squared squared. So we can get rid of the squares here and here. And that will just give us E equals MC squared. Now, again, it's worth repeating that E equals MC squared only applies to an object that is at rest. Only if there's no momentum at all will we get the total energy of an object equals MC squared. So again, MC squared should be thought of as the rest energy of an object. If the object is moving, then it's going to have some additional energy on top of that. That's the idea. So if we take a closer look at this energy-momentum relationship, which is E squared equals P times C, quantity squared, plus M times C squared, quantity squared. Again, this relates the momentum and the total energy of an object in relativity. This has the form of the Pythagorean theorem, right? The Pythagorean theorem says if you have a right triangle, A squared plus B squared equals C squared. This has the same exact form as the Pythagorean theorem, except instead of lengths, we're talking about amounts of energy. And so we can take this equation and interpret it geometrically. So we can construct a right triangle where the hypotenuse, the long side of that triangle, is E. That's our total energy. Now remember, E can be written also as gamma times MC squared. So these are the same thing. We're talking about the total energy as the hypotenuse. The adjacent side is MC squared. And that's what we call our rest energy. So E naught, rest energy, is equal to MC squared. And then the opposite side is the momentum, P, times the speed of light, P times C. So these form the three sides of a right triangle. The hypotenuse is the total energy. And we also have some angle, theta, in that triangle. So this is what we call the relativistic triangle. So let's do an example where we make calculations using this relativistic triangle. How fast would an object have to be moving for the angle theta in this triangle to be equal to 45 degrees? So let's work this out. Okay, so we'll start by drawing the triangle. We have a right angle here. Angle theta is right here. The hypotenuse is the total energy E. The opposite side is P times C, that's momentum times the speed of light. And then the adjacent side is the rest energy E naught. Okay, so if we take the cosine of the angle theta in this triangle, that would be the adjacent side divided by the hypotenuse, which would be E naught, the rest energy divided by E, which is the total energy. But remember, the rest energy E naught, which is on top, is just equal to MC squared, whereas the total energy is given by gamma times mc squared. So again, this is rest energy on top, and then total energy on the bottom. So the total energy also includes kinetic. Now, what we can do is cancel out the mc squared to give us cosine theta is just 1 over gamma. All right, so in this case, cosine theta is cosine of 45 degrees, which is the square root of 2 over 2. And then also gamma is equal to 1 over 1 minus v squared over c squared. We're trying to find v. We want to know how fast this thing is moving. So if we take cosine theta equals 1 over gamma, that gives us root 2 over 2. That's cosine of the angle theta. And that equals 1 over gamma, which is the square root of 1 minus v squared over c squared. So let's square both sides because we want to solve for v. So now I'm going to have root 2 over 2 squared equals 1 minus v squared over c squared. And here, I'll just write root 2 over 2 when we square that is just a half. All right? Okay, so we're almost there. Let's add v squared over c squared to both sides. And then let's subtract 1/2 from both sides. So we have v squared over c squared is equal to 1 minus a half, which is just a half. So v squared is equal to a half times c squared. Now we just need to take the square root of both sides to tell us that v is equal to the square root of a half times c, which is the same as root 2 over 2 times c, which is in decimal form about 0.707 c, or 70% of the speed of light, approximately. Okay, so that's how this works. So let's take what we've learned about relativistic energy and momentum and try to see what we can say about moving at light speed. So remember, the total energy of a moving object is given by gamma mc squared. The momentum is given by gamma times mv, and then the gamma factor is 1 over the square root of 1 minus v squared over c squared. So the first thing to notice is that if an object's speed approaches the speed of light, if v approaches c, then our gamma factor is going to approach 1 divided by the square root of 1 minus 1. So we're going to have 0 in the denominator. The gamma factor is going to blow up to infinity. So if any object has a non-zero mass, if m is not equal to 0, and the gamma factor is blowing up to infinity, that means both energy and momentum would need to be infinity in order to move at light speed. So of course that's impossible. We can't have infinite energy and infinite momentum for an object. That's telling us that an object with mass can't move at the speed of light. Okay? It would require an infinite amount of energy and an infinite amount of momentum. That's not possible. But there is sort of a loophole in this equation. What if the mass is actually equal to 0? Well, then we'll have something that's blowing up to infinity, gamma, multiplying m, which is going to 0. Under the right circumstances, that can equal a finite number. So the only way it could be possible for an object to actually move at light speed is if that object has 0 mass. In fact, any object moving at light speed must have 0 mass. So if we take that a step further and go to our relativistic triangle, where we have, again, the total energy is the hypotenuse, the opposite side is p times c, and the adjacent side is m times c squared. What's happening in this triangle as we take the mass to 0? Well, that means this side right here, the adjacent side, is going to 0. And that means the angle theta in our triangle is going to 90 degrees. So as we take the mass to 0, the angle goes to 90 degrees. So for a massless particle, something with 0 mass, here's what we have. Sine of our angle, theta, is equal to P times C, that's the opposite side, divided by E, that's the adjacent side. But the sine of the angle theta is going to 1, sine of 90 is equal to 1, for a massless particle. So therefore, E is just equal to P times C for a particle with no mass, okay? And this, of course, would include things like photons, particles of light. The energy would be given by the momentum times C. That's for a massless particle. And so that takes us to the momentum of light. Now, Einstein realized that light can't just be simply explained as a wave. He realized that there are many properties of light that can really only be explained by treating the light as a stream of particles, which are called photons. The energy of each one of these photons, each one of these particles of light, was found to be given by this formula, where E is equal to h times F. Now, h is a fundamental constant of nature. It's called Planck's constant. It's equal to 6.626 times 10 to the minus 34 joules times seconds. This is a constant you see in the equations of quantum mechanics popping up all the time, but it's a fundamental constant of nature for our purposes. And then F is the frequency of the light, measured in hertz. So the idea here is if you know the frequency of the light, you automatically know the energy of one of those photons. Now, even though these photons, these particles of light, have no mass, they still carry momentum, which can be transferred to other objects. So if a photon bumps into something, it can actually transfer momentum to that object, and that's important. In Newtonian physics, if you have an object with no mass, if m is equal to 0, it can't have any momentum. But in relativity, massless particles like photons still have momentum. And the relationship between the energy and the momentum of a photon is the momentum P is equal to E divided by C. Again, be careful with how you use this. This, strictly speaking, applies to photons. Now, one way we can take advantage of the fact that light carries momentum is in what's called a solar sail. So if you have a spacecraft with a very large reflective surface that's pointing towards the sun, it's going to have a whole bunch of photons hitting that surface and reflecting off of it. All of those photons carry momentum. So every time a photon bounces off the solar sail, it transfers some momentum to it. And we can actually use that to power the spacecraft, to make it accelerate and move faster. Okay, that's the idea behind a solar sail. So let's take a look at a quick example here. The energy of particles is commonly measured in units of electron volts, where 1 electron volt, or 1 eV, is equivalent to 1.60 times 10 to the minus 19 joules. So if you've taken physics 46, you know what an electron volt is. This is the amount of energy that an electron will gain if it crosses a potential difference of 1 volt. If you don't know what that means, don't worry. You'll learn about that in physics 46. For now, it's just an amount of energy. Okay, so let's say we have a photon, which is moving through empty space, which has a frequency of 4.50 times 10 to the 14 hertz. First, let's calculate the wavelength of this photon in nanometers. Then let's calculate the energy of this photon, both in units of joules and electron volts. And then finally, let's calculate the momentum of the photon in units of kilograms times meters per second. It's the SI unit of momentum, and then also electron volts divided by C. So one thing we're going to need to know here is that the energy of a photon is h times F, where F is the frequency, and h is Planck's constant, which is given here. So pause the video, try to work this out, and then we'll go through it together. Okay, so we'll start by remembering that the speed of a wave, in this case c, is equal to wavelength lambda times frequency f. And what we can do here is rearrange this to solve for the wavelength lambda, which would be the speed c divided by the frequency f. Now the speed of light is 3.00 times 10 to the 8 meters per second, whereas in this case the frequency is 4.50 times 10 to the 14 hertz. And remember, hertz is the same as inverse seconds, or 1 over seconds. So the units we'll be left with here are just meters. If you calculate this, you'll get 6.6666 repeating times 10 to the minus 7 meters. We'll keep 3 sig figs on that. And if we convert this to nanometers, that would be 667 nanometers. The next thing we can take a look at is the energy. So how much energy does this photon have? Well, that's just h times f. H is Planck's constant. That's 6.626 times 10 to the minus 34. The units are joules times seconds here. We're going to take that and multiply by the frequency, which is 4.50, 10 to the 14. Inverse seconds are the units, so notice how the seconds cancel once again, and we're just left with joules. This is 2.981 times 10 to the minus 19 joules, but we'll keep 3 sig figs and round that to 2.98, 10 to the minus 19 joules. Okay, if we want to convert this to electron volts, remember we have 2.981, 10 to the minus 19 joules. And in every 1 electron volt, we have 1.60 times 10 to the minus 19 joules. That's the conversion. So in electron volts, this would be 1.86 electron volts. So typically visible light is a couple electron volts in terms of the energy of each photon. Okay, and then finally, we'll remember that for light, there is a relationship between the momentum and the energy of each photon. And that is P is equal to E divided by C. Okay, so we'll start by doing this in the SI unit of kilograms meters per second. So E, the energy is 2.981 times 10 to the minus 19 joules. But let's remember that a joule is a kilogram times a meter squared per second squared. That's equivalent to a joule. And C is 3.00 times 10 to the 8 meters per second. So basically, unit-wise, we're going to be left with kilograms on top, meters per second. And this works out to 9.94 times 10 to the minus 28 kilograms meters per second. Now, there's another way we can do this. We can take the energy and use electron volts instead of joules as the unit, so 1.86 eV. And then instead of plugging in an actual number for C, we'll just leave that symbolically as C, and we can just as easily say the momentum is 1.86 eV divided by C. Okay, so that's how you do that. And let's do an example problem dealing with a solar sail. So solar sails are made from thin metallic surfaces which reflect light rather than surfaces that absorb light. So the first question for you is conceptual. Why is it better to have a reflective surface rather than something that absorbs light to propel a spacecraft? And then as a follow-up, let's say you have a spacecraft with a mass of 1,750 kilograms, and you want to accelerate it from rest to a final speed of 1.95 times 10 to the 4 meters per second. The photons, that is the particles of light that hit your solar sail, each have an energy of 4 times 10 to the minus 19 joules. How many photons would need to reflect off the solar sail in order to get the spacecraft to that final speed. So when you do this calculation, assume that the incoming photons that hit the sail have the same exact energy as the reflected photons that bounce back. This is a little bit inaccurate. In reality, there's going to be a slight energy loss after the photons reflect off, but just ignore that for simplicity. Okay, so to do this, you're going to need to know again that P, the momentum of each photon, is equal to the energy divided by the speed of light, c. So pause the video, see if you can work this out, and then we'll go through it together. Okay, so let's start by comparing two different things. We can have photons being absorbed by the solar sail or being reflected off the solar sail. So let's try to understand what the difference there is. So if photons are absorbed, this is what that looks like. We have a photon, which we typically label with the symbol gamma, and the photon is moving this way towards our ship, and it has momentum. Let's call that P gamma. So here's our ship. And so the ship would be moving in the same direction, and its momentum would be PS for the ship. So this would be the initial state before the photon actually hits the ship. But in the final state, the photon is absorbed. There is no more photon, it's gone. And all we have is the ship moving forward with an increased momentum. Let's call that PS prime. So again, photon is gone in the final state. It's been absorbed. And so if we assume that momentum is conserved in this process, that means the total momentum of the photon and the ship in the initial state equals the final momentum of the ship after the photon gets absorbed. So what we have is P gamma plus PS is equal to PS prime. Okay? And if we rearrange this to say PS prime minus PS, okay, that will be just by subtracting PS from both sides, that will equal P gamma. Well, PS prime minus PS can be thought of as the change in momentum, delta P, for the ship. So in other words, we have the change in momentum of the ship is just equal to the momentum of that incoming photon. That makes sense, right? We increase the momentum of the ship by however much momentum the incoming photon had. And as we've seen, the momentum of a photon is written as its energy divided by c. And here, if we set up a coordinate system where the x direction is to the right, then we'd put an I hat unit vector to denote that the increase in momentum is in the x direction. Okay, so this is the momentum gained by the ship for every photon that is absorbed. Okay? Now let's look at the case where the photons are reflected. So this is what it looks like when we have photons being reflected off the ship. So in the initial state, we have a photon coming towards the ship with momentum P gamma, and then the ship moving forward with momentum PS, okay? But then, in the final state, after that photon has reflected off the ship, now it's moving back the other way with momentum P gamma prime, That's how we'll call it. And the ship is now moving forward with a different momentum, which we'll call PS prime, just like before. Okay, so that's what it looks like when a photon reflects off the ship. Again, momentum is conserved. Which gives us the initial momentum is P gamma plus PS. Final momentum is P gamma prime plus PS prime. And these are all vectors, so we'll account for the directions later. Okay, so if we rearrange the equation so that on one side I have PS prime minus PS. On the other side of the equation, I'm going to have P gamma minus P gamma prime. And of course, what we have here is the change in momentum of the ship, which we'll call delta PS. That's going to be, again, P gamma minus P gamma prime. Okay, so what is the momentum of the photon P gamma initially? Well, it's moving to the right. That's the positive x direction. And the momentum is E over C. And then we'll have I hat. But then we're going to subtract the momentum of the photon in the final state, P gamma prime. And basically, that's just moving in the negative x direction. So we have negative E over C times I hat for its final momentum. And here we're assuming that the energy is the same before and after, okay? So that actually gives us 2 times E over C times I hat. So notice that the momentum gained by the ship for every photon that is reflected is actually 2 times bigger than if we absorb the photons, okay? I'm comparing, this is the momentum we get transferred to the ship when photons are absorbed. This is what we get when photons are reflected. So it's 2 times bigger if we have the photons be reflected. So that's why you want a solar sail that reflects the light rather than absorbing it, because you can get more momentum that way. Okay, so with that said, what we found is with each photon reflected, the ship gains 2 times E over C momentum. Okay, but if there are n photons hitting the ship, then the total momentum gained is just going to be given by delta P total, that's the total momentum gained by the ship, is going to equal n, the number of photons that hit it and reflect off the sail, times 2E over C. Okay, so that would be the total momentum, not just for one photon, but for n photons. Okay. And then, yeah, we have the I hat unit vector coming along for that. Okay, well, what is the total momentum change of the ship? Well, it's going to be the final momentum of the ship minus the initial. So for the final momentum, I'm going to write that as the mass of the ship times its final velocity, and it's moving in the x direction, so we have I hat. Okay, for the initial, we have 0. So that's the change in momentum. Now, notice how I'm using a non-relativistic formula here for the ship. that's actually okay because even when it reaches its top speed, it's moving much, much slower than the speed of light. So that's actually valid to do. And again, on the other side, we have 2 times E times N over C. And we're going to go ahead and figure out N. So N, if we solve for that, is equal to M, that's the mass of the ship, times V final, that's the final speed it reaches, times C, divided by 2 times E, where E is the energy of each photon. Now, if we plug in what we know, the mass of the ship, 1,750 kilograms. V final is 1.95, 10 to the 4 meters per second. And then C is 3.00, 10 to the 8 meters per second, divided by 2 times the energy of each photon, which is 4 times 10 to the minus 19 joules. Okay. So this works out to 1.279 with 3 sig figs times 10 to the 34. And it's actually just a number. Okay, there's no units attached to it. It's just a number of photons. And if we round it to 3 sig figs, it's 1.28 10 to the 34 photons. Which makes sense because you're going to need a ridiculous number of these tiny particles of light to actually reflect off this ship, which is fairly massive, in order to get it to accelerate to this speed, okay? So again, that's the number of photons that must hit the solar sail to accelerate it from 0 to the final speed of 1.95 times 10 to the 4 meters per second. So the last thing we'll touch on in this lecture is general relativity. Now, this is a pretty advanced topic. We're not really even going to get into any of the equations. I just want to give you an appreciation for some of the concepts in general relativity and how they relate to what we've learned so far. So, when it comes to Einstein's theory of relativity, we actually have 2 versions of it. One of them is called special relativity, which I'm going to call SR from here on out, and the other is called general relativity, which I'll call GR. Now, what Einstein's theory of relativity is about, in a nutshell, is how do we switch between frames of reference? How do I take a description of what's going on in one frame of reference and then translate that to another frame of reference? Einstein was a genius in terms of being able to see things from 2 different frames of reference and relating those. So, special relativity, which was formulated in 1905, deals with inertial reference frames. That is, frames of reference that are moving at constant velocity. So it gives us a way of switching between frames of reference that are moving at constant velocity. And that's everything we've discussed so far. General relativity was formulated about 10 years after that in 1915, and it deals with non-inertial reference frames. So now we're going to account for the fact that our frame of reference can be accelerating. Okay, that's what general relativity is about in a nutshell. But also, Einstein showed that gravity and acceleration are equivalent to each other in some sense. So if I'm accelerating or if I'm in a gravitational field, those are really the same situation. So general relativity, in addition to being a theory about accelerating reference frames, is also a theory about gravity. Okay? That's the idea behind GR. Now, in order to understand that, we have to discuss the equivalence principle. So again, this is the idea that being in a gravitational field and being in an accelerating reference frame are really the same thing. So let's imagine 2 scenarios here. We have Isaac Newton trapped in a box, which is on Earth, where there is a uniform gravitational field. As we know, G is equal to 9.8 meters per second squared on Earth. So that's the situation that Newton is in. Albert Einstein is in a different box, which is moving through empty space. There is no gravity here in Einstein's box, but the box itself is accelerating at a rate of 9.8 meters per second squared. And so we'll also stipulate that these boxes don't have any windows. So Newton can't just look out the window and say, I'm on Earth. Einstein can't just look out the window and say, I must be in space. If they're going to figure out which box they're in, they're going to have to try something else. So the question is there anything that either of them can do to figure out which box they're in? Is there any sort of experiment they can do inside of their box to figure out which one they're in? And it turns out the answer is no. Every single thing that would happen in Newton's box also happens in Einstein's box. In other words, these are completely equivalent situations from the standpoint of physics. They're physically identical situations. In other words, being in a uniformly accelerating frame, like this, is physically equivalent to being in a uniform gravitational field, like this. That's what Einstein realized. So to go a little bit deeper into this, let's think about some potential experiments that each person could perform to try to figure out which box they're in. Okay, so one thing you could do is you could drop an object. Maybe we'll drop an apple in our box. And of course, what Newton would see, Newton sees the apple fall to the floor. And it accelerates to the floor at a rate of 9.8 meters per second squared. Now, what does Einstein see if he drops an apple in his box? Well, he actually sees the same thing. He still sees the apple fall to the floor at the rate his box is accelerating, which is 9.8 meters per second squared. So let's sketch this out a little bit. If we're looking at this from the outside, what we'd say is, well, the apple is dropped and there's no force acting on it, but the floor, the entire box is accelerating up. So the floor is accelerating up towards the apple, right? But if you're inside the box, all you see is the apple accelerating towards the floor, right? There's not really a difference in terms of what you would see inside of the box. So it looks the same as what Newton sees. Okay, another thing you could try to do is maybe stand on a scale and measure your weight. So for Newton, this is what that would look like. Let's draw a free body diagram of Newton standing on a scale. You would have the force from the scale pushing up on Newton's feet, and then you'd have the force of gravity pulling down like this. And the force from the scale is what the scale reads. So this is what the scale will read when you stand on it. And if we apply Newton's second law, F equals ma, well, what we have is the force from the scale going up minus the force of gravity going down, and then that equals 0 because Newton is not moving. So the force from the scale is just balancing out the force of gravity. So the force from the scale is just equal to m times g. Okay? But in Einstein's box, here's what's happening. Remember, there is no gravity. There's just the force from the scale that he's standing on. Okay? There's no gravity, just the force of the scale pushing up on his feet, Fs. So we apply F equals ma, and there's only one force, which is Fs, but now we don't want to say the acceleration is 0 because, of course, the acceleration is upwards like this. So what we get is the force from the scale is equal to the mass times the acceleration. And if A is equal to g, which is 9.8 meters per second squared, then the scale reads exactly what you'd expect it to if you were just standing on Earth. So there's really nothing we can do. If you drop something, it undergoes free fall, just like you'd expect. If you stand on a scale, it indicates that you have some weight, just like you'd expect. There's actually nothing you can do to figure out which box you're in. Every single experiment you perform has the same outcome in the accelerating box and in the gravitational box. So that's why these are equivalent situations. Okay, so next I'm going to tell you about something called Ehrenfest's paradox. So this is a thought experiment that really helps us understand how we should think about general relativity. It helps us sort of build the concepts that underlie the theory of general relativity. So this is the situation. We have a disk with radius r0, and the circumference of that disk is given by 2 times pi times the radius. So we'll call that circumference c0. That's 2 pi times r0. So we take this disk and we fix it to an axle that goes through its center. So that way we can get it to start rotating. So let's say that the disk is now rotating with angular velocity omega. So omega tells us how many radians per second is the disk sweeping out as it rotates. That's omega. Okay, well, one thing we should notice is that the rim of the disk, the outer rim of the disk, is moving at a speed, a linear speed, which is equal to omega times r0. You may remember this from physics 45. If we have an angular speed omega, the linear speed in meters per second is given by that omega times the radius. So if we want to know how many meters per second is the outer rim of the disk moving through, that would just be omega times r0. Okay, so next, we have this effect that we learned about called length contraction. According to the theory of special relativity, we should have length contraction along the direction of motion. So the outer rim of the disk is moving in this direction, like tangent to the circle. That means we should see the circumference of the disk become contracted. We always get length contraction along the direction of motion. That means the circumference, if we're viewing it from above like this, is contracted. So now the circumference is less than c0. It's less than 2 pi times r0. And if we want to exactly say what the contracted length is, remember the formula is the contracted length is the proper length times the square root of 1 minus v squared over c squared. So here the contracted length for the circumference is c. That's equal to the proper circumference c0 times the square root of 1 minus v is omega times r0 squared over c squared. Okay? But the point is this is something less than c0. It's contracted. Okay, so here's where the paradox comes in. The radius of the disk is perpendicular to the direction of motion, right? The disk is moving this way, but the radius is perpendicular to that. So there is no length contraction perpendicular to the direction of motion. So the radius actually doesn't change. So what's going on here? How is it possible that the radius stayed the same, but at the same time, the circumference of the disk got smaller? Is that even possible? Or did we just find some sort of flaw in the theory of relativity? Did we sort of like break the theory of relativity? Well, the answer is no. Actually, all of this can make sense. Ehrenfest's paradox can be resolved if we rethink our assumptions about geometry. Okay, so what I want to show you is that it is possible for a disk to have a circumference c that's less than 2 pi r, not equal to it, but less than 2 pi r, if that disk is embedded, if it's inside of a curved space. So let me show you what this is all about. So we'll start with flat space over here. So imagine drawing different shapes onto a flat sheet of paper. We could draw a triangle. And we would know that the angles in that triangle have to add up to 180 degrees. We could draw a circle. We could measure its radius, and we could measure its circumference. And we'd find that the circumference is equal to 2 times pi times r. we could also take 2 points, one here and one here, and we could ask, what is the shortest path between those 2 points? Well, it's a straight line. Okay, we could look at 2 parallel lines like this, and we could ask the question, do they ever intersect with each other? And the answer would be no. Parallel lines will never intersect. So these are some basic facts that we know about geometry that apply to flat space. Now let me show you a curved space. So instead of drawing these shapes onto a flat sheet of paper, let's say, what if we were drawing these same shapes onto the surface of a sphere? Okay? Now, if I draw a triangle onto the surface of the sphere, the sum of the angles in the triangle is no longer 180. It's actually greater than that. And if I draw 2 points on the sphere, the shortest path between them, it can't be a straight line. It's going to have to be some kind of arc on that sphere. And here, if I draw 2 parallel lines on a sphere like this, actually they do end up intersecting if I follow them far enough along. And then finally, if I draw a circle onto the sphere, the circumference of that circle is not equal to 2 pi r. It's less than that, okay? So these weird things that are happening with the geometry in Ehrenfest paradox can be explained if we just say, well, it's not flat space, it's curved space that the disk is embedded in, okay? So we can resolve all this by thinking about curved space. And so, of course, the Earth itself is a sphere, and we're all living on the surface of that sphere. So we can look at a globe as a good way of illustrating some of these weird geometrical properties of this curved space. So the first one I want to point out is the fact that parallel lines do intersect if we look at them on the surface of this sphere. So here, I'm going to point out this line. This is a line of longitude. So it goes from the South Pole all the way to the North Pole. And here's a neighboring line of longitude. And if we look at them right here, they appear to be parallel to one another. Okay, these appear to be parallel lines. But if we follow them all the way up, we see that they get closer and closer together, and they actually meet at the North Pole. So we just saw 2 parallel lines intersecting. That can happen on a curved surface like this. It can't happen in flat space, but it can happen here. Another thing I want to show you is that the angles in a triangle don't have to add up to 180 degrees. In fact, I'm going to show you a triangle where the angles add up to 270 degrees. Okay, here's how we're going to construct it. So we're going to start at the North Pole right here. And then we're going to work our way down to the equator, okay? And then we're going to turn and start heading this way along the equator. So I think we'd agree that the angle between this line and this line is 90 degrees, right? So now let's follow this line a quarter of the way around the Earth until we get here. And then let's now turn and go north again and follow that line to the North Pole. So I think we'd also agree that the angle between this line and this line is 90. But if we go to the top of the North Pole, the original line I followed and the one we just looked at are also at 90 degrees. Add those together. We have 3 90-degree angles forming a triangle adding up to 270. That's another thing that can happen in this curved space. And so understanding geometry in curved spaces is really the key to understanding general relativity. So in general relativity, space is not just some backdrop where things happen. Space itself is dynamic. It can be distorted. It can be stretched, specifically by the presence of mass and energy. So if we just have perfectly empty space with nothing in it, then space will be flat. But as soon as you put some mass or energy into that space, it becomes curved. And what that means is objects that would normally just travel in a straight line are now going to follow curved paths. So that's how we think about, let's say, a satellite orbiting the Earth. The Earth creates a curvature in the space around it, And now the satellite has to move in that curved space. So again, rather than just moving in a straight line, it's moving along this curve, which looks to us like a circular orbit. There's also curvature in time. And what that means is the presence of mass or energy causes time dilation. So time dilation is something we've seen before. It's not only caused by motion, but it's also caused by the presence of mass or energy. It's also caused by gravity. So Einstein was able to take all of these ideas and encapsulate them in his field equations. So the field equations are shown right here. Basically what's going on is on the left-hand side, we have a term that describes the curvature of space-time. Then here on the right side, we have a bunch of constants, but notice the speed of light comes into play, and also the gravitational constant comes into play. And then this is an object that describes how mass and energy are distributed throughout space. So basically, if you know how mass and energy are distributed throughout space, you can figure out what the curvature of space-time is. Then you know that objects that move in that curved space-time have to follow certain paths, and you can figure out the motion of things like a satellite orbiting the Earth. That's just one example. So there's a quote that I'd like to share with you by John Archibald Wheeler, famous physicist, who really boiled general relativity down to its essence. He said that mass tells space-time how to curve, and space-time tells mass how to move. That pretty much sums it up right there. So now that we've seen the basic idea behind general relativity, I want to show you some of the most interesting consequences of that theory. And we're going to start with something called gravitational lensing, or the way that light rays can be bent by gravity. So to set this up, let's think about this scenario shown in this diagram. So this person is inside of an elevator, which can move up or down from our perspective, whereas this person is outside of the elevator and is at rest from our perspective. So when the elevator comes by, this guy is going to shine a laser beam into the elevator, and this person is going to observe what happens to that laser beam. Okay, so if there's no motion, this isn't very interesting. All we see is the laser beam goes horizontally across the elevator and then hits the wall over here. Now what happens if the elevator is moving up with a constant velocity? Well, that laser beam will still be seen to move in a straight line, but it will be angled downwards somewhat. Now, if we think about the elevator undergoing constant acceleration, this is where it gets interesting. Now this light beam is actually going to curve as it goes across the elevator, at least from the perspective of this person. Okay, so the person in that accelerating reference frame is going to see the light beam curve as it moves across the elevator. But remember, being in an accelerating reference frame like this is equivalent to being in a gravitational field. So that tells us that a light ray traveling in a gravitational field should also curve in the same way that we see here. And that's what we call gravitational lensing. General relativity predicts that the path of light is always going to be bent when it passes by a massive object like a star. And the reason this happens is the massive object will curve the space around it, causing the path that light takes to bend. And so that's the idea behind gravitational lensing. Gravity can have the same effect that a lens does, bending the path of light rays. So this was first observed during a solar eclipse in 1919 by Sir Arthur Eddington. And basically the experiment that Eddington did confirmed one of the predictions made by Einstein's theory. And this is how that experiment basically went. There was a solar eclipse, so the moon was covering the sun at the time of the experiment, and there was a star that was known to be behind the sun during that eclipse. So in other words, there was no line of sight from that star to us because the sun was blocking it. So we shouldn't really expect to see that star, because if light just travels in a straight line from that star,
there's just no way it can reach us because it's being blocked by the sun. On the other hand, if gravitational lensing is a real effect, then that light can be bent around the sun and still reach us. And in fact, it will appear, again, even though the actual position of the star is behind the sun, that the star is actually somewhere else, over here. So the result of Eddington's experiment was, yes, we could actually see that star that was known to be behind the sun, and that's happening because the light is being lensed by the sun's gravity, bending its path. And that really confirms this prediction made by General Relativity. So in the last 100 years or so, since Eddington's experiment, we've discovered many, many other examples of gravitational lensing events with modern telescopes. And I'm going to show you a few of those examples. These are images taken by the Hubble Space Telescope. And you can follow this link if you want to see more images like this. What's going on in this image on the left is we have a spiral galaxy in the background and an elliptical galaxy in the foreground. So in order for light from the spiral galaxy to actually get to us, it has to first bend around this elliptical galaxy in the foreground. And the effect of that lensing is to distort the image of the spiral galaxy that we see. And there's something very similar going on in this image on the right, except what we have are 4 different images of the galaxy in the background being produced. So these are not actually 4 different objects that we're seeing. Instead, these are 4 different images of the same object in the background, which is being gravitationally lensed by a very massive object in the foreground. And this pattern is what we call the Einstein cross. And gravitational lensing has proved to be a very useful tool for studying the universe. Among other things, gravitational lensing has been used to detect dark matter. Dark matter is the hidden mass in galaxies that isn't emitting light, but we can tell it's there because of the gravitational effect it has. So one way we can detect dark matter, at least indirectly, is through its gravitational lensing effect. So another really interesting consequence of general relativity is gravitational time dilation. So this is the idea that gravity actually affects the passage of time. Specifically, if you have a clock that's in a stronger gravitational field, it's going to tick slower. It's going to run slower than a clock in a weaker gravitational field. So this comic kind of spells out what's going on. We have this person who's at sea level, and we have this other person who's standing on top of a mountain. Now, gravity actually gets weaker as you get further away from the surface of the Earth. It's not a big effect, but it is true that this person at sea level is in a stronger gravitational field than this person on top of the mountain. And as a result of that, this person's clock at sea level is going to tick slower. It's going to run slower than this person's clock. That difference is what we call gravitational time dilation. So at this point, gravitational time dilation is a very well-established fact. It's been tested out experimentally many times, and it works exactly how Einstein predicted. We now have very, very precise clocks called atomic clocks that we can use to measure very small amounts of time dilation. In fact, we can now measure differences in time between 2 atomic clocks that differ in height by just 1 foot. So if you have an atomic clock and then another one that's just a foot above it, there's a very slight difference in the strength of gravity between those 2 clocks, and we can measure the time dilation that results from that. So this effect of gravitational time dilation has been used as a plot device in many different science fiction books and movies. One of the most famous examples is the movie Interstellar. So in this movie, there's a character that goes to investigate a planet that's very close to a black hole. So this person spends a few hours near a black hole, whereas their partner was back on a spaceship which is farther away from the black hole. So one character is in a very strong gravitational field, the other person is in a comparatively weaker gravitational field. And as a result of that, the person who spent time near the black hole aged more slowly than the person back on the spaceship. And surprisingly, when they met back up, for the person who spent time near the black hole, only about a few hours had passed, whereas for the person back on the spaceship, several decades had passed. And according to Einstein's theory of relativity, that's accurate. That could actually happen. So another really interesting consequence of general relativity is gravitational waves. So let's think back to chapter 15 when we first studied waves. So first of all, any wave is created by a disturbance in a medium. And that disturbance causes the wave to propagate through the medium at some speed. So that's how sound waves work. That's how waves on a string work. Basically, every type of wave can be described in this way. So in general relativity, the medium is not any sort of material, but space-time itself. And the disturbance is when you have accelerating mass in that medium. So when you have a mass that jiggles around or shakes back and forth or accelerates in any way, a gravitational wave gets sent out. This is a pattern of oscillations in space-time itself that moves through space-time at the speed of light. So Einstein predicted that we should have gravitational waves back in 1916 when he was working out some of the consequences of his theory, but it took 100 years before anyone actually observed gravitational waves for the first time. And the source of those gravitational waves that were detected by LIGO in 2016 were from a merging binary black hole system located over 1 billion light years away. So in a very distant galaxy, about 1 billion light years away, there was a binary black hole system. That means two black holes orbiting each other at a very close distance. While they orbit, they give off gravitational waves, and as a result, they lose energy. So they spiral in closer to one another, and they continue giving off gravitational waves, and then they keep getting closer. At some point, they actually merge. They crash into each other and become a single black hole. When that happens, the gravitational waves become very strong, and they're so strong that we can detect them over 1 billion light years away. So this event happened about 1 billion years ago because it took 1 billion years for those gravitational waves to actually travel to us from that very distant galaxy. So this is how the LIGO experiment basically works. LIGO stands for Laser Interferometer Gravitational Wave Observatory. So I'm going to show you an animation that explains how LIGO works. So first, we have a very powerful laser which sends a beam this way towards a beam splitter. So this is a beam splitter. It splits the beam in half. Half of the laser beam goes this way along this arm, and the other half goes this way along this arm. At the end of each arm of the interferometer, we have a mirror. So the beam reflects off that mirror and comes back the way it came. And then it comes back to the beam splitter where the beams can combine and we can detect the intensity of that beam that comes back using this detector here. So under normal circumstances, when the beams recombine, they will be completely out of phase. So they'll essentially cancel each other out and we won't see any intensity here. But if a gravitational wave comes by, it distorts space and it actually changes the distances between these arms and the beam splitter. And that causes the waves that would normally be out of phase to go back in phase. And so we see, instead of zero intensity, some kind of non-zero intensity at the detector. So here's how this works. We've got the laser beam, goes through the splitter, goes down each arm, reflects back, and then it recombines here. And again, normally we'd have those waves canceling out. But if a gravitational wave comes by, it changes the distance between those mirrors, and it can make the waves go back in phase. And so now we'll see some kind of signal there in the detector when the waves go back in phase. That's what we use to detect the gravitational waves coming through. So back in 2016, there were actually two different sites that had pretty much identical setups to what I showed you here, and each one was capable of detecting gravitational waves. One of them was in Washington, the other one was in Louisiana, and each one of them independently observed the same signal. So that gives us very strong evidence that this was real and not just some kind of statistical fluke. Nowadays, we have even more sites online to independently verify these detections. So I'm going to show you some of the data from this 2016 LIGO detection. First, let's take a look at this graph on the top here, which shows us on the vertical axis the amount that the mirror in the interferometer has moved. And on the horizontal axis, it's showing us time. Now this basically looks like a sine wave, but if we follow it along, we see that the frequency is increasing. The reason for that is, this is showing us the gravitational wave that's being detected. The source of that wave is two merging black holes. So as they spiral in closer together, the frequency that they're spiraling in with increases, and we see that reflected with an increase in the frequency of the gravitational waves they're emitting. Then at some point, they actually merge together and become one, and after that, the gravitational waves basically die off. That's what we see here. Now, based on that data, scientists were able to reconstruct how the velocity of the black holes and the separation of the black holes changed over time. So that's what we see in this bottom graph. So on this axis, we have velocity, which is given as a fraction of the speed of light. And on this axis, we have the separation of the two black holes. So the black line shows us their separation, how close they are, and the green line shows us their velocity. So basically what's happening is they're getting closer together over time, the black line is going down, and their velocities are increasing until they merge together. And notice the velocities are very, very large, very close to the speed of light, in fact. Now, based on all of this data and this reconstruction of the velocity and the separation, scientists were able to determine that the two merging black holes had the following masses. One of them was about 29 times the mass of the sun, and the other one about 36 times the mass of the sun. Now, I'm going to leave you a link here at the bottom of the page. You can actually listen to the LIGO signal if you follow this link. In other words, we can take this sine wave that we see and turn it into an audio waveform and listen to the sound of those merging black holes. And in fact, I'll just play this for you right now. That's what we get when we take this LIGO signal and convert it into audio. And so, as usual, I have a bunch of practice problems at the end of the lecture, so I highly encourage you to try these out, do them for extra practice, especially as you study for the final exam. But we'll end this video here. So as always, I hope you're doing well out there. Hope you're staying safe and healthy. Take care. I'll see you in the next one.